Hello students, welcome back. We just went through an intercept problems and there are some more. Find all intercepts, and here's a curve, and this curve is an example of an ellipse. Indeed, it's an ellipse. And how do you find out the x-intercept? By plugging in y equal to 0. So if I plug in y equal to 0, what do we get? That drops out, right? 0 squared. So that one drops out. So I get x squared over 9 is equal to 1. Let me increase the font. Consequently, x squared is equal to 9. X is plus or minus 3. Look at the picture. Plus 3 right here, minus 3 right there. Makes sense? How about the next example here? Plug in x equal to 0 and so for y. That'll give me the y-intercepts. So plugging in x equal to 0 right here, that's 0. So that one drops out. What do you get? You get y squared over 4 is equal to 1. Y squared is equal to 4. Therefore, y is plus or minus 2. Positive 2 right here. Negative 2 right there. So everything fits. By the way, this is an example of an ellipse. And if you're already familiar with some conic sections and other analytic geometry, great. If you haven't heard about any of those, please consider this as a preview of what's to come. Now, another topic, another conic section, hyperbola. Let me show you the picture. Looks like this. We have one curve and another curve kind of symmetrically distributed like this. Anyway, let's look for the intercepts. Plug in y equal to 0 for x-intercepts. So y equal to 0 there, so that's 0, so that part drops out. What do you get? X squared over 9 is equal to 1, x squared is 9, so x is plus or minus 3. Go back to the picture. Positive 3 is right here. Negative 3 is right there. They fit. Let's go to the picture. Looks like there's no y-intercept here. Nothing to cut through. Indeed. It'll turn out there is no y-intercept. Let's check. Plug in x equal to 0. X equal to 0 right there, so that part drops out. What do you get? Negative y squared over 4 is equal to negative 1. So y squared is equal to negative 4, and that's impossible. You see, for any real number, square is always positive. At worst, it should be 0. 0 squared is 0. We got y squared is negative 4. Therefore, y is plus or minus 2i. Well, that's imaginary. So we don't see anything here. So no y-intercept. Here's still another example of a conic section. Again, if you heard about those conic sections and analytic geometry, great. But if you haven't, please consider these as just a preview of what's to come. And depending upon what kind of topic, what kind of track you are in, but if you are going through teacher preparations for math teachers, either for middle school or high school, you have to learn these. But otherwise, you don't have to. That's why I'm not putting too much emphasis on it. The majority of students really do not need analytic geometry. So let me just show you some pictures and just move on. Here's an example of so-called parabola. And x squared is equal to 4y. That's an example. And let's find out x and y-intercept. Plug in x equal to 0 to find out the y-intercept. Y equal to 0. Okay, that's a y-intercept right over here. And then plug in y equal to 0, and you get, well, the right hand side is 0, so we get x squared is equal to 0, so x equal to 0. Again, we have this point over there. So x-intercept, y-intercept, those are y equal to 0, x equal to 0, respectively. If you like the coordinate expression, you could write 0, 0. There are other examples as well, but as a matter of fact, example we did over here in previous video were comprehensive enough. And then we went through some conic sections, so that'll have to be okay. Now let's go to another topic, symmetry. And there are two types of symmetry that we want to consider here. Basic symmetries, which is 90%, and then diagonal symmetries, which we'll come back and discuss a couple of months later. Basic symmetries first. Symmetry by the x-axis, and algebraically is replacing y by negative y. Symmetry by x-axis, symmetry by y-axis, next one, replacing x by negative x. And then symmetry by the origin, replacing x by negative x and y by negative y. Let's see some examples. Okay, here we go. X squared plus x cubed y squared minus 3y squared is equal to 1. Okay, let's say this curve is here. And then before showing you the picture, let's do some algebraic work. Let's check symmetry with respect to the x-axis. How do we check? Replace y by negative y. Here's another y here, so that 2 becomes negative y. And then simplify. Negatives both disappear because we have even powers. Y squared or negative y squared, the same. So did you get the same thing as before? Yes, indeed. So that proves replacing y and negative y will give me same thing. So symmetry with respect to the x-axis, and then here's the picture. So y is over here, say about 2. Negative y, flip it down there, here. So if I replace y by negative y, means this point go over here, that point come down here. They're still in the same curve. Same thing goes here. Y is over here and negative y is the other side, and vice versa. Y is here, negative y is down there, and then they're still in the same curve because of the symmetry. How about the next example? Replace x by negative x. Do we have the same thing? Well, here's an example. Oh, same curve. Okay, let me use the same curve there. And then, does it look like symmetric with respect to the y-axis? Flip it over to the left. Do we have the same thing? Certainly not. And let's check those algebraically. Replace x by negative x. So replace this x by negative x. And replace this x by negative x. And then simplify. This one's okay because negative power, so we get x squared. This one's not okay. We have extra negative sign there. So did you get the same thing as before? First equation versus the last equation. The answer is no. Close, but we have sign change. So these are two different equations. So answer is no. And confirmed by this picture. Third example, replacing x by negative x, y by negative y. So symmetric with respect to the x-axis, y-axis, both of them put together. And then we're going to get symmetry by the origin. Well, let's see. Here's an example. X squared minus 3 is equal to y squared minus 2. And replace both x and y by negative x and negative y, respectively. And please note that all these are even powers, so they all disappear. All these negative signs disappear. And we get the same thing as before. That means the picture is symmetric with respect to the origin, and indeed. Here's the origin, and then take the mirror image with respect to this, not the mirror image, symmetry with respect to points. So any point here, and then draw a line running through the origin, in opposite place in the same distance. We have to have the point of the curve. Same thing everywhere. Symmetric with respect to the origin. Not a mirror image or folding. Oh, by the way, this picture, this one, it has all three symmetries, all three basic symmetries. Symmetric with respect to x-axis, y-axis, and origin, all three of them. Those are basic symmetries. Do we have an example? Okay, here's an example. Test for symmetries. And this time, let's use graph of a function. Y equals 3x to the 4th power. Let me increase the font. There are fractions here. And the 4x squared minus 2 over x squared plus 1. Okay. Replace x by negative x. What do we get? It's the same thing as before. You see, we have all the even powers. Replace y by negative y. In that case, you're not going to get the same thing. If you change both, you're not going to get the same thing. Those two are left to the students. And here's graphical expression here. And what do you see? We have symmetry with respect to the y-axis. If you fold this graphic paper, then right-hand side will perfectly match the left-hand side. Or you can consider this as a mirror image. Either way, you can see the symmetry. Symmetric with respect to y-axis. How about the next example here? Similar, numerator is exactly the same, but denominator, I change it to x cubed plus x. Will that change something? Yes, indeed. It'll turn out if you replace x by negative x, you don't really see anything there. And you're going to get two different functions. But here, if you change x by negative x, also y by negative y, and simplify, indeed. You see, this negative 1 here, and these are negative of this previous denominator. So those two negatives cancel out, or you can multiply negative 1 to both sides. Either way, you get the same thing as before. And this picture confirms the symmetry. Symmetric with respect to the origin. So draw line segment, draw any line segment. You'll see a point right at the opposite side from same distance from the origin. We have another point, corresponding point. Okay, all right. That's for symmetry with respect to the origin. And how about this one? Actually, we have all three symmetries. So replacing x by negative x, replacing y by negative y, replacing both x and y by negative x and negative y respectively, we have all three symmetries. Here's a picture. Okay, we went through some examples as well. There are some more examples on my math lab homeworks. Now let's talk just a little bit about diagonal symmetries, which probably will not appear for another couple of months. But, well, let's spend about a couple of minutes of class time. It's not going to hurt. I'm not going to write any diagonal symmetry problems yet. A couple of months later I will, but not yet. Anyway, there are two diagonal symmetries. One is important, one is not important. Let's talk about one of the important one here. And switch x and y and simplify. Do we end up with the same thing as before? Then, yes, symmetric with respect to the diagonal x equals to y. Please note that this is x equals to y. And if you fold this graphic paper with respect to this diagonal, fold it over, we'll have a perfect match. And look at this. Algebraically, switch x and y turned out to be the same thing because multiplication is just commutative. This is just one example. There are many examples. Those are diagonal symmetries. And by the way, if I do that, x-axis goes to y-axis, y-axis comes to x-axis. So basically, folding over means switching x and y values. And the other diagonal is not that important, so I'm not going to talk about it. I just left it in my notebook, but de-emphasized in gray. It's just for interested students only. Thank you.